A master's degree in nuclear engineering in 1964 and a PhD in aerospace engineering in 1971. From 1973 to 1980, he was a professor of physics at the Air Force Academy. And then from 1980 to 82, he was the Air Force Chief Scientist of the European Office of Aerospace Research and Development. He was a nuclear research officer at the Air Force Weapons Laboratory between 1982 and 1985. He conducted research on the laser triggered switch and developed techniques for density and temperature measurement on laser-induced plasmas. In 1985, Dr. Pendleton began his work as a professor of aerospace studies at Georgia Institute of Technology. And in 1988, he moved to North Georgia College as a professor of physics. He taught math and science at Douglas County High Schools until he retired. And he has published articles on a variety of professional journals. Dr. Pendleton has spent 25 years giving astronomy lectures and holding star parties. He's always interested in audience questions and skepticism of his ideas. Let us welcome Dr. Pendleton.
Well, thank you very much for inviting me here. I always love coming back to a college campus. I miss that environment tremendously, so I appreciate being here. I wish I could spend some time with you. I have been tasked by my own astronomy club in a month. I have to answer in 5 minutes everything we need to know about neutrinos, where they're created, why they're important, and how to measure them. And that's where I wish I could spend some time with you. I'm sure you know a whole lot more than I do about that. So my first question is, were any of you here a couple of years ago? If you remember, I was here and I gave a talk about black holes. Okay. On the table is an updated handout. And if those are all gone when you leave and you'd like a handout about black holes, you can take, if there's none left, just put your name and email on there and I'll just send it to you. The problem with black holes that I'm updating is the fact that we are finding supermassive black holes that are like 60 billion times the mass of the sun. And we really only know for sure how to make black holes that are about 1 solar mass. And the question is, these new supermassive black holes are very young. They occurred very early in the universe. And there doesn't seem to be any time for a conventional black hole to have grown that big that quickly. So my paper, when I presented it 2 years ago, I thought that was an original idea that I'd come up with. And then I learned that like 70 years ago, John Wheeler, who worked on the Manhattan Project, a very famous physicist, proposed a possibility of how that could have happened. And he proposed that since light is affected by gravity, Einstein's eclipse experiment showed that, well, maybe photons are attracted to each other. And if you start with a big ball of a lot of photons, like the universe in this side of this room, the photons are very dense, very close together. They might condense spontaneously and become black holes. And you can make black holes that are very, very tiny when the universe is small. And as the universe expands, you can make bigger and bigger and more massive black holes. It's counterintuitive. You would think massive black holes would be created when there was most dense, but that's just kind of the opposite. So anyway, if you're interested in one of those papers or you want to get the whole paper, I've kind of updated it and confess that what I thought was an original idea was really not. So I'm not an expert on Gaia. I was asked to give a talk. I live in a retirement community and we do classes for each other. And I needed to do an 1.5-hour presentation on something astronomy. So I picked this. So all I know is what I've gotten off the internet. So if any of you have some more detailed knowledge or you want to challenge anything that I've come up with, I'm perfectly welcome to have you raise your hand and say, well, I see it differently, or add to the discussion. I hope you will. So Gaia is sponsored and basically run by the European Space Agency. I'm pretty sure the data that they're collecting is probably spread all over the world, and most universities probably have a little piece of data that they are analyzing. Gaia, the name is kind of a misnomer, is left over from the original intent of the observatory. It's a global, which means it's going to survey the entire sky. It's not going to be like Hubble looking through a soda straw. It's going to survey the whole visible universe. So it's global. It's astrometric, which means it's measuring things that it looks at, not just looking at them, but actually measuring things. And I'll talk about that. The misnomer is that originally it was going to use interferometry to do those measurements. They decided along the way not to do that, but they kept the name just because people were familiar with the name. And then the last A is astrophysics. So the purpose, which I will emphasize, I'm not going to talk a whole lot about the details of the telescope. I'm going to talk more about some of the results. So first of all, you're all familiar with, whoops, oh, there we go, Hubble. You're familiar with James Webb, and you're familiar with Spitzer. These look like sort of conventional telescopes. Well, Gaia doesn't look anything like a conventional telescope, and we'll go into that and explain why in a minute. But these last two that I mentioned do have something in common with Gaia, and that is, where is it located? It's located at point L2. These are Lagrangian points. And whenever I get to a diagram of the universe, I have to point out it's totally out of scale. The distance, let's see, I don't know if I can get this pointer to work. No, it's not on the screen.
Scroll off to the right.
Oh, way off to the right. Oh, there we go. Yeah. The distance from the sun to the, oops, I didn't want to do that. The distance from the sun to the earth is 93 million miles. The distance from the earth to L2 is only 1 million miles. So you can see it's totally out of scale. Here's the point of these 5 Lagrangian points. They all stay relative to the earth as they all rotate around the sun. A couple of these Lagrangian points are not stable. You can put something there and they will drift away. L2 happens to be one of the more stable places. So if you put a telescope at L2, it pretty well stays there. And the advantage of being that far away from the Earth for a telescope like Gaia and Spitzer and Webb, it is looking at a lot of infrared light, heat radiation. So you need to be far away from a heat source like the Earth. You'd also like to be shielded away from the sun. So there's an advantage to being at L2, among other things. This is the blue orbit there is sort of the orbit that Webb takes around that L2 point. You don't want to put everything exactly at that single point, because you put too many telescopes there, they start running into each other and they interfere with each other. So you orbit them around that point, and it has some advantage. The green one is the figure that the Gaia undertakes. Now I'm going to show you a cartoon. It is not a photograph. It's a cartoon. I want to see if anybody can figure out what it is. It's relevant to what I just told you. First one to raise your hands gets to explain what you think that is. What does that represent? Okay, time's up.
Looks like eclipse.
It is an eclipse. There's the answer. It's actually 3 eclipses. The large black circle, or the white ring, is the sun as seen from L2. You're looking back toward the Earth. the Earth is directly between you and the sun, and it's always there. So you have a perpetual annular eclipse. It's always there throughout the whole year. The two little black bumps on there are what the moon would look like. The large bump in the upper left is what the moon would look like when it eclipses the sun. It spends most of its time being behind the Earth, so you don't see it. But as it gets into that annulus, you can see it poke its way across. The smaller one is also the moon, but that's on the other side of the Earth when the moon is smaller in angular size. So when it eclipses the sun, it does that little bump. I made this up myself. I've not seen this online. I've showed it to a number of my astronomy friends. They have a hard time figuring it out, as you did. And but no one has objected to it yet. It's a simple high school geometry. You can figure this out. The angular size of the sun and the Earth and the moons, and knowing that it's always in that place. So there's a kind of a picture. That's not the location of the Gaia, but that's kind of what it looks like. It doesn't look like much of in the way of a telescope. It's about 10 meters. That shield, the big ring there is the shield, and the telescope is in that little cylindrical black box sort of thing, and we'll talk about that in a minute. Won't spend much time on this. I don't know if I can point this out. There is the size of, there is the size of Gaia. It's a little tiny sliver there. The one underneath it is the Webb telescope in size. The one just to the right of the Webb on the lower left is the Hubble telescope. And these other telescopes are by and large ground-based telescopes of various sizes. Some of them are being built now. Some of them exist already. The one that I like is this big one here. That is a proposed telescope. Can you imagine a telescope that big? Well, it's not been built or funded, and I think they've abandoned the idea. So there's another picture of it. We're going to go inside. As I said, I'm not going to spend a lot of time on this, but I'm going to tell you what basically how it works. There are two main mirrors here, this one and this one. One of them is looking at that out in that part of the universe, and simultaneously, this was looking out at another direction. And that whole assembly is rotating once every 6 hours. So it's taking a stripe of the universe every 6 hours, and then it moves over to another stripe around the universe. And in 63 days, roughly 2 months, it's able to take pictures of the whole sky. That's why it's global. It takes pictures of the whole sky. Well, the light comes in and you can follow the path. It hits that mirror, and that mirror is not very big. It's like a meter or so by half a meter. We're looking at things that we'll see in a minute, mostly things in the Milky Way. So you're not looking at very far distant things that are extremely dim. So you don't need as much light as, say, the Webb telescope, which is looking far into space. So the mirror is of moderate size, and it bounces off a couple of mirrors here. And it ends up over here. This is the detector, basically. And without going into a lot of detail, you all have one of these in your modern cameras, CCD detectors, and what you have, like 5 megapixels or so, something like that, in a pretty good modern camera. This camera has 1 billion pixels, which means it can do a lot finer detail. You know, as your pixels go up, the fidelity of your cameras gets better and better. So this has 1 billion pixels. And so when it takes a picture of a piece of the sky, it has extremely good resolution. So that's one of its functions. That's one of its main functions, is to just take photographs of the stars or whatever's in that field of view. The other part is here. This looks like a bunch of filters and prisms. That takes that light, a part of the light of that object that you're looking at, that region of the sky, and it sorts out every image into its spectrum. So there's another set of detectors that is measuring the spectrum. And that's what those pixels there that's illustrated there. That's all I need to really tell you, because now I'm going to look at what it has found. So that's about as much about the telescope as you're going to get. Okay, so the next. Here is one of the amazing things that Gaia has discovered. You may recognize this. The vertical axis is this is an old chart. This is 100 years old, roughly. 100 years ago or so, Hertzberg and Russell independently started measuring, because we could now figure out how far away stars were, do photography and parallax and that sort of thing. And so once you do that and you can measure the parent brightness of an object, you can calculate what its absolute brightness is, sort of its absolute magnitude. And they were also able to measure spectrum. And so they measured blue stars and red stars, and they pretty well quickly figured out a blue star was very hot, red stars are not as hot. So this diagram is the absolute brightness of a given star, and on the horizontal scale is basically its temperature. And there's a couple of hundred dots on there, which is pretty good for that time of thing, but these were all things that could be measured their distance to, and at that time, you could only measure things out to 30 or 40 light years away, and there are quite a few stars within that range. So here is an HR diagram that's 100 years old. And in particular, there's two of those guys down there. That is a part of an HR diagram, which are white dwarfs. They're not very bright because they're on the lower part of the scale, and they're on the left, which means they're very hot. And they're not very bright, mainly because they're very small. And I've got some pictures of that in a minute. Now I'm going to show you what Gaia's HR diagram looks like. Every one of those dots is a measurement that they had to do to measure its apparent brightness and its distance, and then they converted it into magnitudes. And the sun is luminosity. We measure everything by comparing to the sun. The sun's luminosity is 1. And you can see that it's right there. And it has a temperature. It's a G star, so it's right there. And that tells you the location on this diagram basically tells you a lot. It not only tells you the temperature of the star, but you look at the whole spectrum and you can figure out what the star is made out of by looking at the lines in the spectrum. But you can also figure out with some analysis, and over the years we've learned how to do this, you can figure out what the mass of a given star on that diagram is, and you can determine what its size is. So this is an idea of what Gaia has been able to determine for us. It's only in operation for 12 years. It's just finished operation. It's done taking data. They haven't released all the data yet. This is only 5 or so years of the real data they've taken. In another 5 years, they're going to release the rest of the data. So I would expect this chart to have 3 times more dots on it when it's all finished. So we've learned a lot. And the thing I want to point out that I think is the most amazing, the original HR had 2 of these down here. Look at that. There are millions of those white dwarfs that we really are just starting to discover. and we measure them, and that's where it goes. So here's what a white dwarf is, just because I'm very interested in black holes and white dwarfs and neutron stars. They're sort of the three things that I like most. That's a white dwarf. It probably has the mass of the sun, because our sun, one of these days, when it runs out of fuel and gets to its stages of being a giant, red giant, it's going to eventually run out of fuel and it will evolve into a white dwarf. And you can see it's got the mass of the sun, but it's got the size of the Earth. If you can imagine that sort of thing. Okay, so this is one thing that Gaia has done. It has discovered a lot more, no new kinds of stars, but it has discovered a lot more stars than we had really ever analyzed before. And I'll show you that in a second. The other thing that it's able to do, it's able to study and find asteroids. And this turns out to be very, very important if you think we want to survive the next big asteroid impact on the Earth. The dinosaurs didn't do a very good job of it, but we have a possibility of being able to prevent it. So, I mean, it's bound to happen one of these days, maybe a million years from now, but we need to know how to avoid another impact like that. So, it's found a lot of asteroids. It's found a lot of small asteroids. And in a minute, I will tell you what they know about these asteroids that's very hard to do and why it's important. Here's another kind of an image. If you take the data, of course, we are buried in the middle of the Milky Way, but that's what the Milky Way might look like if you stood outside of it and took Gaia's data and looked back on it. Gaia not only is studying what's in the Milky Way, all the stars and clusters and nebulas and white dwarfs and all that, it's actually able to see a lot of things outside of the Milky Way. So we won't go into that. I'm sort of known around when I give these talks, I kind of have a reputation of coming up with really simple-minded analogies to try to explain difficult things in terms that most of us laymen can understand. And here is kind of a way to think about what Gaia is doing. Imagine you're a tourist in a helicopter and you are flying around on top of a zoo. And you're looking down on the zoo, and you have just got this brand new phone with this great camera, and you just can't, as a tourist, we've all done it, you started taking pictures out of the helicopter onto the zoo. And you take a picture every second, because they're free, right? It didn't cost anything to develop them. So you're taking a picture every second for an hour, that's 3,600 pictures, and you're going to get home, and you're going to get your friends, come over and say, hey, look at my vacation pictures. And what are you going to do? You're going to show all 3,600 of them, right? Well, here's what Gaia is doing. It's taking a picture, a picture, and over 12 years, it's taken maybe 1 million pictures. And the idea is to compare those pictures from day by day, and the pictures will tell you the same thing you would learn from your helicopter. You look down, what do you see? You see maybe 1,000 people at the zoo. You're looking at the zoo. You see people, zoo, different size people, different age people, different masses of people, and your clever camera with your computer analysis can tell what the mass, what the age, what the sex, what the racial distribution of those people is. And that's what Gaia is doing. It's looking at these stars and classifying them. Is it a red giant? Is it a white dwarf? Is it a neutron star? Is it a galaxy? What is it exactly we're looking at? Furthermore, by comparing your pictures day by day, and this is an amazing thing that Gaia is doing, you can determine the motion of each of those people down there. In over an hour, you see they're wandering all around the zoo. So you can track what those objects are doing. And that is a major thing that Gaia is doing. It's taken so many pictures and you analyze them. You now can get the motion of the objects in the Milky Way and see how they're moving. That's a major part of what they were designed to do. The other thing, and I was imagining this, I'm going to show you a picture in the middle that illustrates this. You notice in your picture, a parking lot, all of a sudden a group of 20 or so people show up in a little group. And they move as a group of stars. They enter the zoo, they walk around the zoo, and after a revolution around the zoo, they leave the zoo and get back on their bus. They were probably a tour group, and they stayed together. And you say, well, that was interesting. And I could tell that by just watching that clump move around. Well, here's what Gaia has discovered. Look at the lower right-hand picture. That is a group of stars, or more than 20 stars there. There's maybe a couple of million stars in that group. And Gaia has determined they're all the same distance away from Gaia, and their motion is in a direction, and they're all headed in the same direction. So they're in a group. And now you use sort of a little sophisticated high school physics, knowing the mass of the galaxy, Milky Way, that's Milky Way. You can sort of figure out where that mass was earlier in time, because you know what it's doing right now, and the laws of physics would tell you where it's been. Well, here's what we determine. You go back 8 billion years ago, the computer says that that group of stars came out of nowhere. It's a galaxy of its own, Sagittarius galaxy. It entered the Milky Way here, 57 billion years. No, 5.7 billion years ago. 3 billion years ago, it left. It came back. It's like that tour group keeps coming back to the zoo day after day after day. And here it is today. And here is probably where it's headed. It's probably going to head there. It's going to spiral around. It may leave and not come back for a long time. So this is kind of an amazing thing. We didn't know, but it's the kind of thing that Gaia is doing. And it can measure all sorts of things, how the spiral arms are moving, what their velocity is. So here's kind of a snapshot of the data so far. These are called early release data. I think this is like 5 or 6 or 7 years after it started taking data. And here's what it has done. It has measured the position, that's up here. It's measured the position of almost 2 billion stars. It's measured the brightness, from which if you know the distance and you know its brightness, you can figure out what its absolute brightness is. And it does it in several colors. There's the blue brightness, there's a colored brightness here, there's the red part of the spectrum. And you put the blue and that purple and that red together, and you can determine what the stars are made out of, and their age, their mass, almost everything you need to know, chemical composition of what that star is. It has found extragalactic sources. Those are extra galaxies in some cases, star clusters out there that are not in the Milky Way. It was designed to study Milky Way stuff, but it's inadvertently discovered almost 2 million other things that are out there. And as I showed you with the tour group going to the zoo, it measures the velocity of an object. Now you can use Doppler radar, or Doppler radar concept to measure the radial velocity or speed of an object. You can just compare pictures from year to year to year, and over 10 years, an object is going to move laterally. It probably won't change much in size or brightness during that time, but it'll change laterally. And you put those two together and you can get the absolute velocity of the objects out there. And that tells us a lot about how the whole Milky Way galaxy behaves. And you can study the motion of other galaxies. So, summary, and a few extra things that might come out. Summary is we're determining the position, the motion, and composition so far of about 2 billion stars. It's going to be another 5 years before they release the rest of the data. So there's probably going to be 3 billion stars by the time they're through releasing all the data. They've determined, they did a lot of that white dwarfs. Remember, there's a lot of white dwarfs there. And their white dwarfs are of different ages. And you can figure out that from exactly where they are on that HR diagram. And they've determined that white dwarfs are basically solid balls. They're very dense. You got the mass of the sun in the size of the Earth. You're going to squeeze things down, and as it cools off, it becomes a giant ball bearing. Is basically where it's headed. And as it cools down, it doesn't have a source of energy, so they expect a white dwarf will gradually drift down to the bottom of the HR diagram, and someday it'll probably be invisible in terms of its brightness. It still has all that gravity, so white dwarfs, even though they're dead and gone and invisible, they have a lot of gravity. If we're looking for dark matter, maybe that's a place to look. There are a lot of them, and most stars end up as white dwarfs. So you're going to have a lot of very cold ball bearings out there that are very hard to detect once they cool off. So Gaia has determined that Milky Way is about 13 billion years old, and it was formed roughly 800 million years after the Big Bang. And if that black hole, we don't know this, the black hole may have occurred last year or the year just before they discovered it, but we suspect, looking at other galaxies far away, that black holes are created very early in a galaxy's life. So we expect the one that's in the center of the Milky Way is also very old. We've discovered a lot of quarks and quasars and all kinds of new stuff, more stuff, not new stuff necessarily, but more stuff. And it showed you that merger of that one galaxy 10 billion years ago. It's pretty well determined that. And we know that galaxies interfere with each other all the time. They're colliding all the time. There are all kinds of pictures of two spiral galaxies that look like that. They've come together and they've meshed together. And if you get some of these together, they will eventually form an elliptical galaxy out of them. It's discovered some hypervelocity stars. Hypervelocity stars are basically stars that are destined to leave the Milky Way, and they'll go off on their own. You just have a close encounter with a heavy star and you can get slingshotted right out of the Milky Way. And they discovered some of these hypervelocity stars, a lot of new asteroids. They're starting to look at exoplanets. They've measured the acceleration of the solar system. We all know from physics, you drop a ball, what's the acceleration of gravity on the Earth? 9.8 meters per second squared. I wrote it down. At least this is one source. Our solar system is revolving around the center of the Milky Way galaxy, right? So that means it's accelerating toward the center of the galaxy, just like the moon is accelerating toward the Earth. It doesn't hit the Earth because it's going around. So here's the measurement that came out Gaia. It's not 98 9.8 meters per second squared, it's 0.23 nanometers per second squared. Nanometer, a billionth of a meter. So it's accelerating 10 billion times less, more or less, than dropping a ball here. So just an interesting number. Near Earth objects, those are those asteroids that come close enough to the Earth so that they're worth being concerned about. We haven't found one that's going to hit yet, but there are projections. There's a pretty good size one out there that might hit another 10 or 20 years. We don't know. The stars roughly are 1% of all the stars in the Milky Way. That's of now. I suspect when we're all done, we'll probably have 2% or so of all the stars in the Milky Way have actually been measured. They'll show up on that HR diagram. And then 99.9% of all these billions of objects have never been measured before to the accuracy that they can measure things. What is that accuracy? How are we doing? We're getting there, right? Still got a little time. Okay. How accurate can you make these measurements? Well, in the HR diagram, about the best they could do was stars that were about a parallax second away. What's that? Well, your thumb is roughly, at arm's length, is roughly 1 degree, more or less. The moon, you won't believe this, but try it the next time you see the moon. The moon is half the size of your thumb. Most audience will tell me the moon is bigger than your thumb, but it isn't. It's about half the size of your thumb, which is about half a degree. So your thumb, that's about 1 degree. Well, a second or a minute of arc is 1/60th of that. A second is 1/60th of that. And the precision of the accuracy in measuring parallax of Gaia is not a second of arc, it's not a millisecond of arc, it's measured in microseconds of arc. That's a billionth of a second, which is 36 hundredths of that. This is extremely accurate. And if you do the math, I kind of checked it, but I'm not accurately sure. It's like the head of a pin on the moon. That's how accurate they can measure the parallax. And if you can measure that parallax to that accuracy, then you can measure the distance and you can measure things further and further and further away. The other thing, I haven't checked this. It seems a little inconceivable, but maybe it's true. And I think when they do more data, they may revise this number. The last one on the list, which was surprising to me, they claim that studying all these stars, just the ones they've studied, 1%, they now estimate that the mass of the Milky Way galaxy is 3 trillion times the mass of the sun. Now, if that's a good number, and if the average star has the mass of the sun, some are a lot bigger, not very many. Most of them are much smaller than the sun or less massive than the sun. You can see that from that HR diagram. They're small, they're less massive. If that's true, the Milky Way contains over 3 trillion stars. And in most textbooks, they say, oh, the Milky Way has 500 billion, 500 million stars. Well, this result seems to say that the mass of the Milky Way is a lot bigger than we thought. And if that's the case, we don't need as much dark matter to explain its rotation. So I think that might end up being a very critical number as we start looking for dark matter and trying to figure out why the galaxy is spinning faster than it should. And maybe it's because there's a lot of stars out there we haven't measured their mass, and there's a lot of small objects that we haven't seen yet that we can explain that. Okay, we have time for questions. And I love questions. For my students, I tell them the only stupid question you can ask is one that I'm too embarrassed to admit that I don't know the answer to. So I'm not embarrassed. If you ask me something I have no idea about, I'll try to find out.
Okay, the last to the second from the bottom bullet point, 99% of objects. Now, Gaia is using a parallax method. Now, I know the old parallax method was to make a measurement on the star in the spring and then another one in the fall.
Same thing.
Next year. It's the same thing. Okay.
Same process.
Yeah, only
you take
a lot more precise.
A lot more precise.
Okay. Yep. Thank you.
Yep. The precision of parallax greatly improved once we started taking photographs of objects, because then you could compare a photograph over 6 months. It's like the example I give with parallax is, if you hold your thumb out and you look up on the screen and you close your left eye and then you close your right eye, or vice versa, your thumb changes location. And if you know how far away the screen is and how big those words are, you can figure out what the angle of shift between right and left eye. If you know the distance between your eyes and you know that angle, high school geometry will tell you the length of your arm. It's the same thing. It's a star. That's probably a couple of degrees, I would say, maybe 6 degrees. And so I can figure out my arm is about 1 meter long. But if you're starting measuring micro arc seconds, that thumb gets way far away. So good question. That's basically the same thing that Henrietta Leavitt did back 100 years ago when she worked for Harvard, and she looked at glass plates. They didn't have CCD detectors and storing these on a computer. They had glass photographic plates taken with a telescope, and they would compare these stars on these plates 6 months apart, and they could tell, oh, that dot just moved a little bit over 6 months. And she figured it out, and she looked at variable stars and determined, looking at Magellan Cloud, where all the stars are basically that far away. She didn't know how far away they were at the time, but they were all the same distance away. And she found variable stars, their magnitude correlated with their brightness, because they were determining the brightness of stars on these plates and their motion, their parallax, which they got the distance to. And she started seeing, oh, these stars not only change position, they change in brightness from day to day to day. And she correlated the period of a variable with its absolute or its apparent brightness. And you got a chart there. And once you do that, Edwin Hubble took that and used that. He found Cepheid variables in Andromeda. And he said, oh, there's a Cepheid variable. I looked at Henrietta's chart. I see what its variation is. I look at her chart, and that tells me how bright it is. If I know how bright it is, it tells me how far away it is. So he used that to determine the distance to these distant galaxies. And that opened up our whole view of the universe. Up until that time, we were confined to studying things in the Milky Way. Now we study things out at the far end of the universe. A good question. Yeah.
Okay, so my question is about another kind of a failed star, a brown dwarf. Does Gaia have any way to see those and quantify the number?
Yeah.
And how much, if so, how much of the material out there does Gaia show that it, what percentage of the material is composed of brown dwarfs?
Well, you sort of get this off this diagram. There's a sun. These stars are all basically smaller, less massive, cooler, than the sun. So you go way down here and you're starting to look at very cool stars that are very small. They're not very bright. And that's where you would find these brown dwarfs. They might be technically not exactly full-fledged stars. They might not be hot enough to be doing nuclear collisions in the center, but they're producing enough energy to be able to see. So that's where they would be. You see on this diagram, most of the stars that Gaia has found are less bright than the sun and cooler than the sun and are older. Some of these stars down here are extremely old. These stars up here have to be pretty young because they don't live very long. They run out of fuel. If you're born here a billion years later, you're probably run out of fuel and you may be down here by then. These guys down here, some of these are original stars that were created 13 billion years ago. And we see a lot of those in globular clusters, which tend to be very old.
We have a Zoom question.
Oh, good.
Ron Rannick asks, if the estimated mass so far of the Milky Way is roughly 3 trillion times the mass of the sun, is it conceivable that some or a significant portion of that mass is dark matter rather than stars, allowing the current estimate of star count in the Milky Way to remain about 400 billion stars?
It's possible, yes. I don't know how that 3 trillion masses arrived. It may have arrived by looking at the motion of the Earth going around the center. So he may be right. He may be that dark matter is a lot of that 3 trillion masses. Could be. But I think a lot of it is these undiscovered and unmeasured stars and very dim objects that we're just very recently being able to observe. So I'm holding out for a lot of black holes that exist in the Milky Way. That's my own personal belief that what dark matter is, because you can make a lot of golf ball size black holes if you go to the early universe, when the density of the universe was roughly the density of a black hole this size. You can make trillions of those, and they would be very hard to see and observe because you wouldn't have things orbiting around them like the one that the Milky Way has. So a lot of black holes out there would be very hard to see. And if there are enough of them, you could conceivably count for all the missing matter. Possibility.
I think that within the last 2 minutes since you were talking, you answered a great deal of my question.
Oh, okay.
Okay, but however, if we even take in consideration the supposed halos that are around all the galaxies, okay, like you said, it could be accumulations of white dwarfs, neutron stars, etc., things that are not really bright enough to see with even the best optical equipment.
Exactly.
And this is what I just sort of wonder if dark matter is going to end up being some type of a farce someday.
It's hard to say what they're going to find. I like particle physics, and I like discovering new macro particles out there that we don't know anything about, but I'm not sure our standard model allows for that yet. Maybe CERN can discover one of these things. And if they discovered the right particle with the right characteristics, and they can figure out there must be quadrillions of these things out there, then you could use those to explain dark matter.
Mm-hmm. You still have.
We know that there's a halo of globular clusters around the Milky Way, and Gaia is studying those also. And in those clusters, those globular clusters, there are a lot of white dwarfs because those are very old stars, and all the stars that were much heavier, or just about the heaviest as the sun when that cluster was originally created, all of those have been converted into white dwarfs, or maybe some novas here and there, and maybe there's some neutron stars that we can't see. But an old group of stars kind of tells you where a lot of this matter ends up. So, and we may
Well, if that
discover
would
more
solve
of it.
dark matter, you'd still have dark energy to worry about.
Yeah. I have my theory of that too, but I don't want to go into it. That's a little less, my thinking is a little less sophisticated than it should be. So we have an astronomy club at Windcrest where I live, and we got 100 members. We've been in existence for about a year now. We meet once a month and we do each other programs like this. I'm doing one next month on magnitudes of where they were originally thought of, and why a large magnitude star is actually dimmer than a first magnitude star, which is the brightest ones, or almost the brightest ones. And they wanted to know what a quasar was. They wanted to know what a pulsar was. They wanted to know what a neutron star was. And then, as I said, they wanted to know what a neutrino was. So I got to do all that in about 30 minutes, which is a tall order. So how are we doing on time?
I think we're
Good place to stop?
Yeah, I think that's all the questions, right? There's no more online.
Okay. So take one of these handouts and put your name if you'd like to know just one more opinion about where some of these supermassive black holes came from.
If one of the online people wants this document that you put together, how do we?
Can I give them my email address?
If you'd like to, yeah.
Live?
Yeah.
Okay, Zoom guys, get your pencils out. It's WPENDLETON, the numeral 8 at Comcast.net. So if you email me and you want to ask a question, you want to keep the conversation going, or if you just want a handout, I'll be glad to take any of your questions.
Great. Thank you.
And thanks very much. I appreciate it.